All right. Hello, everybody. To the few people who are watching, and to the people who will be in here in a minute, and the people who will be watching this later. Welcome to session 4 of my character materials and rendering workshop. In this session, I'm going to be talking about everything normal mapping. Everything from what the hell a normal actually is, to how you can bake normals, to what the different types of normal maps are. I'm going to be going over a variety of different topics, including what actually a normal itself is, what normal maps are, how the different channels in normal maps affect shading, what the differences are between tangent space normal maps and object space normal maps, what tangent space and object space mean. I'm going to talk a little bit about how you can author normal maps, how you can create them, whether it be by baking it from a high poly object, painting it in Photoshop. I'm going to talk just a little bit about something called swizzling, which has to do with how the color channels are ordered and rendered. I'm going to talk about the differences between using object space and tangent space normals, using hard and soft edges with normal maps. I'm going to talk about triangulation and how it affects shading. I'm going to talk a little bit about bent normal maps and how you can use them, how they can be used in production, and how you can use them for things other than normal mapping. And I'm going to talk just a little bit more about bit depth and normal maps. It's basically just to touch on some things that I mentioned in I believe the second session when I was talking about things like compression, MIP maps, and different file formats, just as sort of a refresher. So let's start at the very beginning and sort of define our terms. What the hell is a normal? Well, that's a it's an either very complicated or very simple question when you get down to it, and it can have a couple of different answers. But the gist of it is that a normal is a line that shoots out from the middle of something. So for our purposes right now, we're going to say that a normal is a line that shoots out from a vertex. So like this vertex right here, you could shoot a line out from that vertex, and depending upon the direction of that line, that part of this plane that I have right here would shade differently. So what does that mean for us as artists? Well, let's take a look at what happens if we change the normals of an object, see how it affects shading, and then see how we can use that to our advantage, or see how that can affect the final result of what we're doing. I'm going to be jumping around between Modo and Marmoset Toolbag a little bit. I might do a little bit of stuff in XNormal, depending upon what if I get any questions in the Twitch chat, anything like that. But in general, I'm mostly just going to be in Marmoset and Modo for this one. This stuff is really independent of whatever program that you're in. As long as you're using a 3D program, you're going to be talking about normals in some sense. Modo is just what I happen to be pretty comfortable with, and it has some pretty okay vertex normal editing tools, so that's why I'm using it right now. But you could do very similar things in 3D Studio Max, Maya, probably Cinema 4D, even though I've never used it. Basically any 3D program out there is going to have tools for editing normals, whether it's face normals, vertex normals, normal maps, anything like that. So, back to the question, what is a normal? Well, let's go over here and turn on Show Vertex Normals. And let's make sure that we have some stuff turn on. So here we have the vertex normals of this subdivided plane. So as you can see, there's a bunch of these little lines that shoot out of the plane, and what these are the average direction of the vertices that make up the intersection between these polygons. You can see here on the corner there's a little line as well. That's just the direction that is basically facing out from the polygon. So a vertex it contains a few different things aside from just a location in 3D space. A vertex contains more than just XYZ coordinates, but it also contains directional information. Now, as you can see, this plane is single-sided, which means that it's all facing upwards. In this case, it's facing along the y-axis. I'm not going to get into the y-up versus z-up debate, which is a thing that exists. It's pointless and stupid, and nobody cares. Regardless, this is facing up along one axis, and you can see that when I click on a single one of these polygons, the 4 vertices that define its corners are pointing upwards, along with all the rest of them. Now, I can change this. I can change which direction these vertices are pointing. And what that's going to do is it's going to change the way that light reacts with this plane. It's going to change the way that light actually reflects off it. So let's do one quick example to show how that works, and then I'll show what's happening with a slightly more illustrative example in the same little scene. So I'm going to select this vertex right here, and I'm going to change its normal. I'm going to change the direction that that normal faces, and you'll see that it changes the way that this thing is shaded. So we're just going to go up to, where was it? Vertex map, and transform normals. So what I can do right now is I can change the direction that that normal is facing. I can rotate it. So the blue line corresponds to the direction that the vertex normal is pointing. And as you can see, depending upon which way I rotate it, it gets more or less lighting information. When it's darker, it gets less information. When it's light, it gets more information. So what does that mean for shading objects? What does that mean for us when we're trying to do something with something that's a little more 3D? How do the vertex normals behave on an object that's slightly more 3D than just a simple plane? Well, let's make a little new object in here and talk about that for a second. We're going to make another plane. We're just going to basically take a cube and delete all the faces we don't want. We're going to put a line down the center of it. Okay, so this is just a very simple plane. Now let's make sure that, yes, show vertex normals is on. We're just going to make a vertex map real quick so that it'll actually show them. Okay, so this has little lines coming out of it along the vertex normals, very similarly to that other thing, the other mesh that we have. But with this one, we're going to actually change the shape of this mesh and see what happens when we change the shape of the mesh instead of the vertex normal. So let's move this up like that. Now, you'll see that all those vertex normals are pointing in the same direction. They're pointing up. Now, the reason for that is because what I did just before I made this little tent shape is I made a vertex map. The vertex map it defines the direction that the vertices are pointing. So that isn't the one that I created is an absolute vertex map, which means that those vertices are always going to point in this specific direction, along the y-axis in this case. But I can change that. I can change the direction that they're facing. And actually, if you have smooth shading turned on for the object that you're working on, you will find that if you transform the object in some way, if you change how it's constructed or how the polygons are laid out, the vertex normals will change. So let's reset that vertex map and see what happens. Okay, so let's go back here and set vertex normals. Yes. Okay. So here's something interesting that's happening. We now have the vertices showing their normals, and they're now pointing outwards. They're now pointing in a direction that corresponds to the direction that this face is pointing. If I set the selection mode to, well, selection, and I try to move this, what it's going to do is it's going to shoot a little line out from the center of the polygon in the direction that the polygon is facing. I can move it along that axis, blah, blah, blah. So that's the direction that these vertex normals are pointed. Cool. Great. However, you'll notice something up here. Along these points, the vertex normals are actually split. You can see that there are two vertex normals on a single point, even though there's only, well, yeah, there's only one point there. What this actually means is that you have two faces, and they're joined together, but only insofar as you will be editing them at the same time. For shading purposes, there are actually two vertices which have two different vertex normals. Now, if you do something like, well, if we go over here and I select this edge and I just tell it to smooth out, what it's going to do is it is going to unify those vertex normals and make it so that it has smooth shading, which is averaged between this face over here and this face over here. So it's taking the shading from the middle of this plane and it's blurring it to make a gradient between that value and the value on this side. Now let's see what this means when we have a light visible. Let's turn on show lights, and it'll be a little more obvious. So let's just move that back a little bit so it's not quite as obscenely bright. Okay, so this makes it a little more obvious. We have a light over there, which is pointing directly at our little tent shape. And you can see that if we turn the vertex normals so that they're all hard, this face is being lit, this face is dark, and if we average them, it averages out the shading between them. You get a nice smooth gradient. So when you're going to edit this, for both shading purposes and editing purposes, this is a single vertex. Now this is something that can be fairly important if you're working with fairly heavy models in a game engine, because anything that has hard edges like this will be processed in a way that has multiple vertices along those edges and at these points. But that's kind of getting ahead of ourselves. Let's go back to talking a little more about vertex normals and what they represent. So now that we have like a basic understanding of what vertex normals are, let's talk about how changing them affects shading. So let's go back to that plane we made. And we still have our light visible, and you can see that there's a little bit of a gradient. It's a spotlight, so it's got kind of a hot spot. So let's change one of these vertex normals. Let's change this one. We'll just go to transform normals. Now the light is over there, and if I transform this normal so that it's pointing away from the light, it's going to get dimmer. And conversely, if I transform it so that it's pointing towards the light, it gets lighter. Now, you're not changing the actual direction that the face is pointing. The face is still pointing up, and you're only going to see it from this side, but you are changing the vertex normal, which changes how it receives light from that light over there. Sweet. Awesome. Cool. How does this help us? Well, since we can actually change the way that individual faces are shaded like this, it also stands to reason that we should be able to change them in the middle of the face. I mean, you could just, say, subdivide this face and get more points in there, and, I mean, in theory, you could just keep doing that and keep doing that until you get all the vertices that you want. You could transform them individually. You can take this one and you can transform it. You can rotate it this way, and you can do that with all of them. or you can use a normal map. So what a normal map does is it applies those same transformations to the normal of the face, to the average color that you get along the entire polygon. It applies those same changes that you see when you transform the vertex normals, but it does it on a per pixel basis based on the pixels of the normal map. So let's take a look at how that can work on our little plane right here. Or actually, I have a similar plane set up that has some nice uniform UVs, and let's load that up into Marmoset Toolbag, like so, and have a look at what we can do, just with very, very simple normal maps. So I'm going to go into Photoshop, and I'm going to paint a normal map. So when you're talking about normal maps, when you're talking about the values in normal maps, it usually becomes pretty clear that each of the color channels corresponds to a different number of some sort. Well, those different numbers correspond to X, Y, and Z coordinates in your 3D program of choice. Let me just turn on the wireframe and brighten that up a bit, just so we can see the edges all the time. There we go. Perfect. Okay. So I'm going to take and I'm going to paint a normal map. And I just want to affect it from, say, left to right. I only want it to be a sort of like curved surface that looks sort of like, oh, maybe if we take a cylinder, I want it to look like, say, this highlighted chunk of the cylinder. I want the normals to look like, oh, hang on a second. I want the normals to have the nice curvature that these curved faces do. I want them to point out and radiate out in directions like that. So how can I do that? Well, if I have a plane, and we can imagine that this texture is a plane, you have up and down, and you have left and right, and if you know that the different color channels correspond to up, down, left, and right in some way, you can then start painting a normal map. So normal maps start out as a sort of neutral bluish purple color. And what this color represents is an unchanged surface. So basically, this plane right here, even though it doesn't have a normal map loaded, it does have a flat normal map applied to it. The normal map that's applied to it is just a single color, and each of the X, Y, and Z coordinates is set to be exactly the same as the vertex normals, or the face normal, which is the average of all the vertex normals. So what you see is the same as the plane that I have over here in Modo. It just looks flat. However, we can change that. In the red channel, if you want to get a nice curve, what you can do is you can have a gradient from red to black. Or from red to black, you like that? From white to black. And the result will end up being something that looks kind of pinkish. So let's make a gradient, and we can show how that affects the shading. So we're going to do a nice black to white gradient. And what that's going to do is it's going to have values that represent directions that are going almost 100% to the left and 100% to the right, but nothing that represents up, down, or any depth. So what exactly does that mean? Let's go back to Modo real quick and take a look at some vertex normals. So basically what we're going to have is values that represent what would happen if I drew a line directly out from over here, directly out from over here, and everything in between. So if I subdivide this, it's going to get all these nice smooth values. That gradient from black to white, or usually actually from white to black, is going to represent that curvature. And the 50% gray value right down the center, or pretty close to the center, is going to represent that neutral value. So let's save this in our examples. And then load it up in a marmoset and take a look at what we can see. So if we load that into the normal map slot, we can see that, well, somehow the normals have changed. It's kind of hard to see, but if we put a light in our scene, like this, and we make sure that it's not too obscenely bright, let's just tone that down a little bit. If we rotate this plane, what we're going to see is a change in shading. Ah, there we go. So you can see that when you apply some color to the different channels of a normal map, it changes the shading. Let's do it with a slightly more exaggerated and or exact example to kind of get a better read on things. Let's undo this. It's back to gray. And let's put a few values from black to white. We'll just do dots of black over here, dots of white over here, and then maybe a little dimmer stuff in between. We'll save that, go back to Marmoset, and there we go. Now we can see that when we change the angle of the plane, the amount of light that each of those spots is receiving is changed because of the values that we put into the normal map. So this is almost identical to rotating your vertex normals in here, except you're doing it on a per pixel basis. So you're not just editing one of these, you're actually editing the texture, which then edits that normal. Okay, so that's the gist of normal maps. They represent different orientations of these normals. Cool. Perfect. Awesome. Why does this work? And why, for example, do we call them tangent normals? You'll hear tangent normals mentioned a lot alongside object space normal maps. So let's talk about tangent space normal maps versus object space normal maps for just a few minutes. Tangent space normal maps represent a change to this surface. They represent this surface having all of these normals and those normals just being changed. By contrast, object space normal maps represent absolute directions in space. So let's take a look at a different example. If we look at this cube, we can say, oh, let me just turn off the light so it stops focusing on there. If we have a cube, we can say that this face corresponds to up, this to down, and then the others to left and right and forward and back. That makes pretty good sense. I mean, it works. That's how cubes are. They're front, back, left, right, up, and down. Now, instead of just having a normal map that affects the vertex normals or something, what you can actually have is a normal map that is not just based on the direction that those vertex normals are pointing, but instead based on absolute coordinates in space, or absolute directions in space, that have really nothing to do with these individual vertices or these faces. They really just have to do with absolute directions. So let's make an object space normal map and see how that can affect things. So I have a high poly here, which has just some really chunky bevels on it, and I have the low poly here, which I had before. So let's bake some some tangent space normals, and then some object space normals, and look at the difference. So if I go here, now there are going to be different ways to bake these out, but the gist of it is that you can do this in anything that you can bake, basically. There are some programs where it's a little more difficult or easy to bake out object space normal maps, but in general, basically any program that you have that can bake normal maps can bake both object and tangent space normals. Alright, so we're going to actually export this cube. Let's just make sure that it's in a plain old scene. We're going to do low 01 for this guy. We'll save it as an object. And we're going to do, high 01 for this guy. And we're going to bake some object and tangent space normals. We're actually going to do it in Marmoset toolbag. I'm not going to get into the nitty-gritty of all the baking and stuff in here. It's not really what this is about, but I'm going to go through the process very quickly just to make sure that it gets done and we can get it out of the way. So we'll just make a new bake group. We will load a couple of objects. Open those up. Put them in the appropriate places. All right. So we got that loaded and that loaded. Okay, let's go to the baker. Let's tell this thing to go here. We're going to say the name is cube. And we're going to bake out a regular tangent space normal map and then an object space normal map. We're going to set the size to something a little lower. So 1024 sounds good. And we're going to bake it. Cool, it's baked. Now we can preview each of these like this. So here we have a tangent space normal map that is applied to the cube. And you'll notice that we have some of that reddish color, or the pink. We have the neutral bluish purple color. And then we have, some greenish blue, some other purple colors, some green. Each of those correspond to the R, G, and B channels that you could see in Photoshop. Now, if we look at the object space normal map, it's going to look very different. So this is baked from the same object to the same object. And you can see that instead of having the sort of neutral bluish purple color, instead what you have is absolute colors corresponding to up, down, left, right, and forward and back. So let's take a look at those maps in Photoshop and see what the differences are. So we're going to open up the tangent space map and the object space map. So same UVs, same objects, different types of shading. Now, if we go into the different channels, here we're viewing all three RGB channels, but if we go into red, we can see that, oh, well, there's the gradient from black to white, and it just has the flat area in the middle, and that's the left and right according to the actual surface of the object. It's relative to the surface of the object. And here we have another gradient This one is for up and down, relative to the object. And then we have a little bit of depth, which is also relative to the surface of the object. Now, by contrast, let's look at the object space normal map. Now, here we have some very different values. Let's take a look at the channels. So we still have those gradients, but instead of it being object space, or instead of it being tangent space, which is relative to the surface of this cube, relative to these different faces, it's just changing that normal. Instead, it's assigning a specific color based on which direction it's facing in 3D space. So this might be a little bit weird. So let's take literally another angle on it. Let's go back to Marmoset and do something a little bit odd here. Let's deliberately misalign our meshes and try this again. So I'm going to rotate the low poly object, and we're going to try baking again. I'm going to make sure that my cage is very large. There we go. So it's going to fully encapsulate the high poly. And now, let's try baking those again and see what the difference is. All right. So you can see that it's changed, but how has it changed? Let's turn off the high poly. Okay. Okay, interesting. Let's take a look at the tangent space map. Okay, so here we have stuff that is relative to the faces of the low poly mesh. So if we turn on the high poly again, we can see that what it's doing is it's taking the direction of the high poly over here and assigning a color to it that makes it so that the shading tries to be as much like the high poly as possible by changing the color. So let's go back in here and just reload these. Update that. Okay. So you notice that these different faces, the faces along, let me turn off the high poly. So the faces along essentially the equator of the low poly object, these ones along the sides, they all look more or less the same. Now this is because the high poly object, it's rotated about 45 degrees off from the high poly object, and each of these faces essentially has the same information on it and has the same information being projected to it. This is relative to the low poly face. There is a thing poking out, so it's trying to capture the information from it. So that's why these things look more or less the same. It's relative to that face, therefore it just puts the same color here, 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 and here. All those faces look more or less identical, so it's just putting pretty much identical information there. Now if we look at the world space, it's a different story. What this is doing is it's taking the same value for the top and the bottom, but then it's putting the values for absolute coordinates, absolute directions, absolute front back, absolute side to side, and projecting them onto the low poly. It's not relative to the faces of the low poly, it's actually looking at the directions of the world or the directions of the high poly and just putting those onto the low poly mesh. Alright, so that's kind of a big weird topic, and it might take a little while for some of it to sink in. That's fine. Normal maps are weird, but we do kind of have to move on. So let's move on to something else and loop back around to this in just a bit. Let's talk about swizzling. Let's talk about how different how different renderers process normal maps. So let's change the transformation of this back to 0, so it's just back where it belongs. Let's rebake this. So it's back to there. So we're just kind of back to neutral. And let's talk about how different environments will render normal maps. So often what you'll see, and let's go back in here, update that, and there we go. So often what you'll see when you are baking a normal map is that when an object is supposed to have a positively curved surface on it, the red channel will have a gradient going from left to right, which is dark to light. And what that's doing is, like we saw before when we were painting this normal map, and I can invert this, save that, and we can reload the plane into here. Let me just get that plane real quick, drag that in there, and just hide that. So let's look at this plane again. Let's put a nice bright light in here. And let's load that normal that we just painted in there. Now let's take a look at this light and the direction that the light is coming from. Now, with stuff painted into the red channel and the light coming from this direction, you can see that that little white arrow is the direction that the light is coming from. It's coming from over on the left side over here. So it's kind of pointing like that towards the plane. You'll see that with this direction being painted over here, this dark value being painted over here, it's treating it as if this part of the face is pointed towards the light, and by that same token, the part that's painted white over here is pointing away. Now, some renderers, some game engines, some offline renderers, etc., they will have that changed because really it's just grayscale information. It's just some numbers that have been plugged in to make grayscale values in these little pixels. Now, the same is true for the green channel. In some renderers, what you'll see is that the light looks like it's coming from above, like this. So it'll look like it's green on top if there's supposed to be a curved surface. Let's save that and go take a look. Let's change the orientation of the light. Or actually, let's just change the orientation of the plane. That's a little easier. So it'll look like the light is coming from above in these channels. So this would be, say, a bevel, kind of like you see the bevel here in the green channel. But there are some other renderers where this is not the case. For example, Unreal 4, it has the green channel set up so that this would be inverted, like so. Now, there's no real difference in how this information works when you have these values inverted, because they're just trying to represent the same thing, except with slightly changed values, just values that are flipped around. That's just an artifact of how Unreal and some other engines render things. So in general, these are defined along the divide of OpenGL or DirectX. OpenGL is an open source format for doing rendering. It's an open source library of programming methods that lets you create game engines and do renders, and you don't have to pay Microsoft anything. Whereas if you use DirectX, it's a very similar technique, a very similar set of tools. The only difference is, at least for most artists, is that the green channel of the normal map will be flipped, or not flipped, but rather inverted. So it's really, you can just press Control-I in Photoshop if you need to get something like that working. So let's take a look at how some different engines render stuff like this. And there's a very handy way to do that in Marmoset. If we go in here into the object's properties, we can change the tangent space to something different. Now, tangent spaces are essentially methods of rendering normal maps and vertex normals that use standardized math. Now, each one is going to be slightly different because there are multiple different ways to render objects in computers. But in general, basically what it means when somebody talks about a tangent space is what math and what equations are being used to get the behavior of this light hitting this object. So let's turn our cube back on. Let's just drag it out here so we can see it a little better. Let's make sure our plane's turned off. Okay. Let's just rotate this so we're not getting weird shadow artifacts. Rotate that as well. Well, we're still getting some, but that's okay. All right. And let's clear that normal map and put this one on. So this is the beveled normal map that we just baked. And you can see that around the edges, it has those kind of soft edges, kind of like the high poly did. So it tried to transfer information from the high poly onto the low poly, and this is the result. This is the resultant shading. Well, this was baked using the Marmoset tangent space. If we change the tangent space that we're using, we're going to see some differences. The biggest difference would be if we switched to something like Maya or 3D Studio Max. So it's going to be the same for Maya, but for 3D Studio Max, now it looks wrong. And this is because the math that 3D Studio Max uses is different from the math that Marmoset uses and Maya uses to calculate normals. So if you wanted to render this cube with this normal map in 3D Studio Max, you would have to either bake it using the 3D Studio Max tangent space, or you'd have to bake it in Marmoset using whatever tangent space, and then convert it to using 3D Studio Max's tangent space. Usually what that entails is flipping one or more of the color channels, which I can do here. If I invert that and save it, oh, well, now the shading looks pretty normal again. But if I change this back to, say, mic/x normal tangent space, which is a widely used tangent space and method of calculating normals, it's going to look wrong again. So you just have to change it back. Now, if we're discussing object space normal maps, this actually is less relevant. Tangent space normal maps rely on the tangent space of the specific renderer to render properly. However, object space normal maps don't have the same restriction because object space normal maps rely specifically on X, Y, and Z directions rather than directions that are relative to the surface of the object. So let's plug that object space normal map into here, switch it to object space, and try playing around with the tangent space. Now it might still present some issues because certain types of rendering will expect that up and down or left and right might be inverted in the map, sort of like we were doing with this map. you might have to flip this around, but you won't get as many rendering artifacts with object-based normal maps simply because they refer to absolute directions as opposed to directions that are based on the calculations of directions out from the surface of this object. So let's try changing the tangent space again. All right, so since this is an object-based normal map, since this is using absolute directions, up is always up, down is always down, left and right are always left and right, blah, 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 changing the tangent space to 3D Studio Max, or to Unity, or to Maya, or to XNormal, or to Marmoset is not going to change anything because these values, these up, down, left, and right, are always up, down, left, and right. Now, since these are always up, down, left, and right, this means something interesting. This means that if you rotate this object, you're not always going to get what you expect. Now, Marmoset is pretty smart in that they know what to do when somebody plugs an object-based normal map into their renderer. Basically what they do is they say, okay, I know what X, Y, and Z was when this object was imported, and I know which direction it was facing. So when I rotate it, it's not going to change stuff. It's going to look, it's not going to change stuff relative to the model. So they do some math under the hood to make it so that it always shades correctly. However, there are some game engines that support object-based normal maps which don't allow you to rotate objects at all. So in that case, what would happen is if I had this cube and I tried to put it into an engine that doesn't support object-based normal maps or doesn't support transforming objects with object-based normal maps, if I had this light pointing in this direction and I rotated the cube so that this face right here was pointing away from the light, like this, it would still receive lighting information from this light because as far as the engine is concerned, with that object-based normal map, that face is still pointing in the same direction it was before. This is not the case with tangent-based normal maps. Tangent-based normal maps always assume that the direction that they're changing is only the direction relative to the surface of the object, as opposed to relative to the environment that they're in. Okay, so that is more or less the entirety of what you need to know to at least get started with tangent space and object-based normal maps. So let's sort of tweak our direction and talk about something a little bit different. Let's talk about using hard and soft edges with normal maps. I'm going to go back to Modo. I'm going to open up this guy, this cube that we just had open, and instead of him having these hard edges on these faces, I'm going to smooth them all out. So as you can see, what it's doing is it's taking the lighting from this face, and the lighting from this face, and it's averaging them all out. It's making it so that you have smooth shading across the entire cube. So let's save this and see what it does to the object in Marmoset. Let's see how it changes the lighting. Let's just close that, reload it, and make sure that we have a tangent space normal map on there. All right. And make sure that we have the channels in the right directions. Okay, cool. Oops. I'm alt-tabbing too quickly. All right. So here's something weird going on. So we smoothed out all the normals, but they're not displaying properly. Now this is actually an error on my part, but this is something that can happen when you try to edit the normals of an object in really weird ways. Sometimes what will happen is the normals will get flipped around because it's possible to rotate normals. Let's turn vertex normal display on. Oops. Oh, I'm sorry. Show vertex normals. Okay, let's turn that on. So sometimes it's actually possible to make it so that these vertices, these vertex normals, are rotated around so that they're, say, inside the object. You probably don't want that. I'm getting an error similar to that, so I'm just going to delete this and do something slightly different with the shading. Modo occasionally does have some smoothing issues, so I'm just going to do things this way. But you can see that in here it just looks the same. So we'll save that, go back in here, and make sure that our skylight is on. Okay. Oh, well, interesting. Let's make a new material and put that on there. Something was wrong with our material. I'm not sure what. Doesn't matter. Well, okay, so we're back in business. Let's turn a light back on. Let's turn shadows off because those are calculated in a way that we don't want to worry about right now. Okay, so you can see, as I said before, that it's trying to average out the values between all the different faces. So things look very smooth, like unnaturally smooth for it being a cube. Let's try baking some stuff again and see what happens in this situation. So let's turn our baking stuff back on, put that in there, adjust the cage. Okay, so that green stuff is our cage. And let's try baking out an object space and a tangent space normal again and see what the difference is. So we'll bake that and take a look at the tangent space normals. It's going to be pretty weird. There's going to be lots of gradients, and I'll explain why in just a second. Okay, so there's the tangent space normal, and here's the object space normal. Tangent space, object space. So, once again, tangent space is relative to the surface of the object. Basically, all you're doing is trying to change the values of this face, or the normals of the individual vertices. But you're doing it on a per pixel level. Now, what Marmoset is trying to do in here is it's trying to take the shading information. Let's put that on there. Not sure why that material got all janky, but that's okay. So it's trying to take the shading information of these nice smooth corners and the large flat areas and transfer this flat shading information on here onto this very smooth shading information on here. You notice that this doesn't have the beveled corners, it's just averaging out the faces. So what it's trying to do is it's trying to put curvature that is opposite to what you see on here to counteract the effect of it being sort of this weird curvy looking surface, and in doing that it ends up putting gradients. So there's lots of gradients in here to counteract the fact that it's averaging between different faces. You can see that in these different channels, in all the channels actually. However, something interesting happens when you take a look at the object space normal map. It looks identical. It looks absolutely identical to the one we had before. Now, once again, this is an example of information being taken from the high poly object with absolute directions and being projected onto the surface of the cube. It doesn't care that the surface of the low poly cube is all smoothed out and stuff. all it cares about is the direction that the high poly mesh is facing at any given point. So all it's doing is it's taking the direction of, well, let's turn on our wireframe so that we can see. It's taking the direction of this big square face and is putting a big square of 100% up on that face, and corresponding directions for all the other faces. It's just 100% in that direction, or 100% in that direction, or 100% up, down, left, right. It doesn't care that this is all smoothed out and it's all averaged, because it's only taking information from the high poly. It's not trying to do an average of the low poly and high poly. So let's take a look at how these different normal maps look when we have this material on here. And I just realized what was happening. I had object space turned on instead of tangent space. Hey! So here's our low poly object. Let's put the tangent space normals onto here. Alright, so you can see that by having all those gradients, it's counteracting all of the curvy surfaces and stuff that it looked like it had before, and it's making it look flat. It makes this entire face look flat by having curves on here, by having gradients in the normal map. If I took this normal map and I painted that normal color along the middle, what you're going to see along the normal of all, or along the middle of all these faces, what you're going to see is this is all going to look very smoothed out like it was before. So let's save that, and there you have it. That curvature, that smoothness is no longer being counteracted, so now it's just back to the way it was. It's back to having the normals pointing out in the directions that they wanted to be before. So it might be a little bit hard to see at the resolution of the stream. However, I'm going to zoom in a little bit and take a look at something. All right. Now as I get closer, you can see it's not just artifacting in the video and the stream. This is actually a bunch of noise in the normal map. Now, what you're seeing here is the fact that we're using an 8-bit normal map, like we mentioned a few days ago. And what it's trying to do is it's trying to interpolate between different values to get something that's a close approximation to the mathematical value that it needs to counteract all that curvy stuff. Now, it only has so many colors that it can play with in the normal map because, like we said before, each of these color channels can only show 256 levels of gray, and they add up to 16.7 million colors. If this was a 16 or 32-bit image, that noisiness would be far less noticeable. So let's actually bake out at a higher bit depth and take a look at that. Let's take a look at how that looks. Let's make sure that we can use hidden meshes. Okay. And we're going to change our format from 8 bits per channel to 16 bits per channel. We're going to undo the changes we made there just so that we have a good comparison. Okay, so we can see the noise. Now, oops, let's bake at 16 bits per channel. And suddenly all of those noisy bits go completely away. So just adding additional bits per channel makes it so that you don't have any more noise in your normal map to try and approximate the right numbers. Now there might be certain instances, depending upon the type of shading that you're using, where with a 16-bit image you would see some noise in the normal map. However, in this specific case, where it's just a cube and it has some flat surfaces, using 16-bit is perfectly adequate. However, if it ends up that you have lots of curvy surfaces that need very subtle, slight curves and such, that's when you might want to, think about using 32 bits per channel, which we can do now. We're not going to see much difference though. the difference is pretty much imperceptible, at least on this model. So let's go back to 8 bits per channel. Bake that out real quick, just so we have a good frame of reference. And now let's try using a different tangent space with this existing normal map and see what happens. Now, as I mentioned before, the different tangent spaces are different methods of calculating the normals of the vertices and the normals of the normal map. So in theory, when we switch to a different tangent space, this model should look different. And this is actually a good test case because baking a beveled cube like this onto a smooth cube is one of the tests that you can use to make sure that your baker is set up the right way. So let's change the tangent space from Marmoset to, say, Unity. All right. Now there's something interesting for you. So even though Unity and Marmoset use the same up, down, left, right as in their normal maps, in their tangent space normal maps, the result looks vastly different. You have this big gray spot right here and stuff. The shadows look kind of weird because the math used to calculate the difference between the high poly and the low poly is different. So since the math used to calculate it is different, how it displays the normal map is also going to be different. So if you ever hear people talking about using synced normal maps in a game engine, this is what they're talking about. You are baking a normal map with math that is synced up to whatever the rendering engine uses. So you're using the same math to calculate the normals in the baker as you are to calculate the display of normal maps in the engine. We can take a look at some of the other tangent spaces as well, just to get some good comparison. Here's Maya. It looks pretty good. Here's X normal. Oh, that doesn't look so good. And here's Marmoset again. Let's take a look at Marmoset and Maya. Oh, they're pretty close. You might not even be able to see a difference in here. Cool. Now, if you're baking for the purpose of importing into something like Unreal Engine 4 or the newest versions of Unity 5, along with many other current generation game engines, you'll find that you will be using either something very similar to the Marmoset tangent space, the Maya tangent space, or the Mic/Xnormal tangent space. Now, Xnormal was written and became popular around the same time that a lot of engines were starting to become a little more modern and use things like physically based rendering, and that's why it's included in here, because it's very easy to use and it's very common. Lots of engines use it. We actually use it at Insomniac as well. Alright, so let's talk about something slightly different. Let's talk about triangulation. Now, triangulation and normal maps go hand in hand in a few ways. I'm going to demonstrate how triangulation can affect normal maps and how triangulation can affect just the vertex normals of something. And for that, I'm actually not going to use a cube, because a cube is not actually the ideal candidate, but I am going to use something a little closer to what you might see in the real world if you're working on a character. I'm going to use a cylinder. A lot of excitement there, let me tell you. Hoo-wee! Okay, let's just close this and close that. Let's close all this stuff. Let's go back to Modo. Let's just make a new object. Let's make a cylinder with just a bunch of sides and one segment. So let's just turn on wireframes here. So here is a very simple cylinder with some nice shading on it. You can see that it's got a nice sharp edge around the top and the bottom. And this center portion of the cylinder is nicely smooth shaded. Okay, well that's awesome. That's perfect, and that's exactly what we need for this demonstration. Now this has 32 sides around here. That's a good number to use just because it's easily divisible by 2 and 4 and 8 and such. But it's also going to be a good example of how using different numbers of polygons on similar objects can affect shading, can affect triangulation, and can affect a few other things. So let's start baking some normal maps for the cylinder and see how triangulation can affect different types of shading. Let's save this as it would help if I could spell it correctly, cylinder low 01, just in case we need more than one low. And then let's bake out, or let's do some nice bevels on here to round out these edges. Okay, cool. So now that's very smooth. And let's save this as cylinder high. Okay, now let's go back to Marmoset and just make a new scene. We don't really need anything fancy for this. All right, we're going to make a new bake group. We're going to load up our meshes and do some baking. Okay, so I'm going to show the UVs here real quick. Oh, looks like we got some overlap in the UVs. That's not going to be too terrible, but it might present some issues. We'll see. We'll see what happens. It'll be a fun adventure. Okay, so let's bake something out. Let's bake this as cylinder 01. We'll bake normals and object-based normals just so we have our nice little complete set. And just hit bake. Now, when we take a look at the object-based normals, it looks very similar to what we had before with the cube, except there's a much smoother gradient around the center. However, the top and the bottom are the same colors that we're used to seeing on that cube. So those are the absolute directions for up and down. If we look at the tangent space normals, we can see that once again it has those gradients where it's trying to average things out and show the difference between the high and low poly, and then everything else that corresponds to the high poly is just flat shaded. So let's load the cylinder normals onto here and take a look. Sweet. Looks great. Looks fantastic. It's nice and smoothed out. Everything looks peachy keen. However, we're going to start running into problems really quick if this is much lower poly, for a few reasons. Let me show you why. So let's just undo some of the changes we made on here. And let's take out some of the polygons on here. So we'll just do this real quick. Get rid of those. We'll go one more. Okay. Now, let's go into shading. We'll make this nice and smooth to accentuate some of the triangulation. All right. So now this has been smoothed out similarly to the cube that we had before. We are averaging out the values on this face, this face, this face, and all the other faces that it touches. We're averaging things out, and we're getting smooth gradients. Okay, cool. So we'll save that. Oops, we'll save that. It's changed so that it has the corresponding number of sides back in Marmoset. And let's rebake this. Oops. Looks like the cage wasn't large enough, so let's just push that out a bit and try baking again. Okay. Well, this is different. This is a very different result that we're getting. Let's go back in here and preview that. Yeah. Oh. So, we've got some interesting stuff going on, both around the edges, here, and on the top. So let's take a look at that normal in Photoshop and see what's happening. Ah, okay. So, you'll notice by looking at this normal map that there's some pretty unexpected stuff happening. Now, we do have the gradients along the edges of the top of the cylinder and the bottom of the cylinder, and it's clearly averaging things out along the top. However, you'll probably notice that there are these weird spikes going across the top in both channels. Both the red and green channel have these kind of odd spikes of color. Now, this is related to triangulation. So let's do something specific so that we can get a better idea of what's going on. Let's triangulate this model. So it's 100% triangles. So it's just drawing triangles along all these surfaces. Let's save that. Go back to Marmoset. Bake again. Now, the direction that Marmoset triangulates things and the direction that Modo triangulates things are different, but they'll produce similar results. So let's go back, reload that normal map, and we're going to see it's not as obvious, but if we do a levels adjustment, we'll be able to see it a little more clearly. Here you can see that you do have some weird spikes in color. So it's doing the same thing, just in a slightly different direction. Additionally, across the red and green channels along the sides, you can see that it has other similar spikes. Now, when we go into Marmoset and we have that texture applied as the normal map, everything looks nice and smooth because it's compensating for all that curvature and stuff. But we can do something to make it so that this is completely screwed up. And it's not going to have to do at all with the normal map. Instead, it's going to have to do with the triangulation. So let's change something in here. Let's change how this is triangulated to see how it affects the normal map. Let's just flip these around. And you know what? We can just we can flip these as well, just to show a better example. So you'll notice if I turn off the wireframe, you can see along here, you get a similar spike to what you see in the normal map. And that's because what it's doing is it's averaging out the shading between all of these touching triangles. All those triangles get averaged out shading based on this vertex right here, along with some other calculation, and you get this weird spike. Now, Marmoset, when it renders out a normal map, along with XNormal or whatever other program you use to bake your normals, it's going to try and compensate for this change in shading. So let's take a look at how that looks in Marmoset when we have the normal map applied, the same normal map. It looks completely wrong. You'll notice that there is this weird X-shaped artifact right in the middle of these faces. And along the top of the cylinder no longer looks like a flat, smooth surface. It just looks wrong. It looks weirdly undulating and stuff. This is because when you render a normal map, the normal map is compensating for the shading that happens when it's triangulated. So what this means is that when you go to render a normal map, or any other map for that matter, you probably want to triangulate your model before you bake it. That will ensure that when Marmoset calculates the triangulation, the algorithm that it uses is not different from the algorithm that the 3 program of your choice uses. Instead, what you're doing is you are controlling all of the directions that these triangles are going so that they're always the same, so that you always get consistent baking results. You won't get those weird X-shaped artifacts, and then you retain much better control. So, you can probably see how this could affect the rendering of a character. So let's load up a character that we had open recently and take a look at how triangulation will affect him. We're going to load up that rock and roll guy, and we're going to change the triangulation on his face so that it doesn't match the triangulation that's being accounted for in the normal map. Let's just hide everything else. Hide this, that, and that. Okay. Let's turn off some of the fancy render effects so that things just go a little faster. And we'll just apply plain old material to him. There we go. That's pretty good. Actually, let's make it so that the shadows are slightly better. And actually, let's just turn shadows off entirely, because that's just going to be annoying. There we go. Nice smooth shading. So you can see along the edges of the light terminator right here, I'm getting some very similar spikes to what I had in the cylinder. Now you can see, if I turn on the wireframes, this area is not actually triangulated. However, because of the way video cards and 3D rendering work, all of these models are being rendered as triangles, which are being just kind of smushed together and rendered as a quad. Oh, it looks like I have a little bit of depth of field on here, so let me just turn that off. There we go. That's slightly better. Okay. So this quad right here, you see this spike going along right here? This is happening because what the video card is doing, what Marmoset is doing with the triangulation, is it's calculating a triangle right here and a triangle right here, and it's averaging out the shading between those two, so you get a little spike right there. Now, if I have the normal map for his face, let me go find that. I just realized I don't have it open right now. Let me get that. It's in here and here. Head normal.psd. Let's drag that in here. And you notice that instead of a really nasty spike, it actually smooths it out a bit. That's because the normal map is accounting for the triangulation of these faces, at least to some extent, and it's rendering them slightly more smoothed out. Now, if I zoom in here, you will notice that the terminator of the light, along with this highlight, they're both very noisy. Now, once again, that's an incidence where it might be best for me to use 16 or 32-bit normals to get rid of some of that noisiness. Because I have some pretty subtle shape changes in here, some large gradients, the normal map isn't doing its best to account for those changes in color, so I'm getting some slight dithering. If I used a 32-bit normal map, if I baked it in 32-bit or in 16-bit, I wouldn't get any of that noisy stuff. So this is sort of a more real-world example of where it can be good to use a 16 or 32-bit texture for your normal map. Now, I also didn't bake the normal map for this guy's head in Marmoset because that simply wasn't an option at the time. It was not a feature they had added yet. I baked it in another software program. So the reason that I still get some triangulation errors, some waviness in my normal map right here, or in my shading rather, is that the tangent space, like I mentioned before, doesn't match exactly. It's close, but it's not perfect. If it was perfect, this would actually be one nice smooth curve. So there's one last thing I'm going to talk about, and it's going to be a little bit more theory, but it's just to give an example of different applications for normal maps and different ways that normal maps can be used, and different ways of using normals to get a map. And that is bent normals. Now, bent normals are kind of weird. They are not they're not what you would call accurate to the actual normals of whatever it is you're trying to render. Rather, they are the normals of something that have been adjusted to render in a slightly different way. So let's do a little diagram here, just to give an example of what a bent normal map is. Now, if you've been doing character art for a little while, or you've looked at tutorials online for how you can do things like stylized rendering, kind of like you might see in World of Warcraft, Heroes of the Storm, Team Fortress 2, etc., you might have heard about things called bent normal maps. Now, there are some pretty good uses for bent normal maps, but one of the best ones is actually in very modern rendering for skin. Now, what exactly is a bent normal map? A bent normal map is an object-based normal map with some modifications to it. And those modifications are made so that you can do better rendering of very high-res details. So let's try something out. Let's say I have a face. Nice happy little face. Woo! Hello, happy face. Now, this face, if you zoom in on his cheek right here, he's going to have a bunch of pores. Those pores are little holes that, if you draw a cross-section, might look like a few different types of shapes. They might look simply like a little dent. They might look like a dent with a big thing at the bottom that's open like that. They might look like a very shallow divot. Each one might be different. However, bent normal maps are best used when you want to capture detail from very fine details like pores and have that detail show up at the right angles. Now, what exactly does that mean? Well, if you have an object-based normal map, you have, say a cube. We're going to view this cube just from the side. And right in the middle of that cube, you have a normal pointing out. Or right in the middle of here, you have the face normal. Over here, you have this face normal. Up here, you have that face normal, etc., etc. Oh, and my tablet's just gone dead. That's handy dandy. Cool. Well, if you have a bent normal map, and or if you have an object-based normal map, and you have a bunch of little pores, some of those pores, like I said before, are going to have little overhangs. So when you try to, when you try to render an object-based normal map, the only surfaces that you are going to see are along here, here, maybe a little bit of this area, and down here. Because what's happening is the low poly object up here is just looking straight down. It's looking down like that. Now, bent normal maps are different in that they try to capture a little bit more of the detail in these curved areas. So how do they do that? Well, what they do is they do not change the normal coming out from the low poly. They actually change the normal coming out from the high poly. So instead of the high poly having normals that go, oh, this is ugly as hell, but it'll illustrate. Instead of the high poly having normals that go straight out like this, and then at angles like this, and then at angles going down, and then curving back up, a bent normal map changes the normals of the high poly so that instead of these normals pointing inwards, they change them so that they go up and up as much as they can until it's able to escape. And then when you project onto your low poly, it's going to look down there, it's going to see this normal and take the absolute direction in world space and project it onto here, and this normal and its absolute direction in world space and project it on here and here. But then it's going to take this normal right here that's trying to escape, this little line trying to get out of there. It's going to look at that and say, oh, I wouldn't normally be able to see that since it's trying to point away from me, but I'm going to bend it until it's close enough to pointing towards me that I can now see it. So what does that mean for both high-end rendering and low-end rendering? Well, for very low-end rendering, like something like World of Warcraft, if you have a fancy knife blade, whoo, that's a fancy blade, and you start carving some divots into it in ZBrush, you're going to be able to get more interesting shading out of those little divots than you would if you were using an object space normal map. It's going to look at all these normals in here and adjust them so that the low poly can see them. Now for high-end rendering, how can you use that since it's not actually representative of what's really there on the high poly? Well, let's get back to our little friend the smiley face and his little pores. If you are working with skin shading that tries to smooth out the normals of your mesh with things like scatter depth, you're not going to get changes to the specular behavior, especially in areas like this. You're not going to get changes to that specular behavior. It'll only be changes to the diffuse behavior. So if you have lots of detail of pores, if you have, say, detail captured that looks like this, as opposed to just detail captured that looks like this, you're going to get much more detail with a bent normal map for your pores than you would otherwise. At glancing angles, you're going to be able to see pore detail much better with a bent normal map than you would with an object space normal map. So, I know it's a pretty weird concept to wrap your brain around. There are several articles that you can look at online that go into much more technical detail about bent normal maps, along with all the other different types of normal maps you can use, and different types of normal map baking, rendering, and usage in game engines. But I hope that that's a good primer for all of you guys. Um, I still have about half an hour left for the general stream before I go to the private hangout with the program members. So if there's anything that you wanted to ask over the next, say, 5 to 10 minutes before I start just shutting things down, since I've covered basically all the topics I wanted to talk about, feel free to use the Twitch chat to ask me some questions, and I'll get to them as I see them. So the question that I have right now is, so then would you use a bent normal map for the detail normal in that case? Actually, that's a very good question. You could use a bent normal map. However, since bent normal maps are very similar to object space normal maps, they don't always work well for detail normals or normals that would be tiled onto your material. So in this case, if you have a bent normal map, you can actually do something like take it into X normal and convert it from an object space normal map to a tangent space normal map, or really a bent normal map to a tangent space normal map, and you'll be able to see that pore detail a lot better in your regular normal map. Now, some renderers and some shaders actually allow you to input a bent normal map, and this is based on a lot of research from say NVIDIA and a lot of high-end research people who have been doing stuff for the next generation of rendering for video games. We're doing a little bit of research into seeing if we can use them at work right now, but it's looking like just current methods of rendering are going to work best for us. But the very highest end game renderers will use bent normals in some capacity to do better skin rendering. So I've got another question. What are the modifications you have to make to the object space normal map to make it bent? Or can you bake it? Yes, you actually can bake a bent normal map. There are different renderers that have different options for bent normal maps. The one that I would recommend using, just since everybody kind of knows it and it's pretty easy to use, is XNormal. Although you can render out bent normal maps, I believe from Maya and 3D Studio Max. I don't recall if Substance Painter supports bent normal maps, but it might be worth looking into. Now, granted, bent normal maps currently are mainly used for very high-end and very low-end rendering, and in low-end rendering, they're actually used so that you can grab detail from them and overlay it onto your diffuse maps. So that's where you would use it in low-end rendering, because it catches some of the smaller details from divots and other stuff that you sculpt in a lot better than an object space normal map would. Are there any other questions that you guys have? Those are some really good questions, and really good start of discussion if you wanted to dive more deeply into that. In case you guys are wondering how you can bake a bent normal map in XNormal, you would load your high definition meshes and low definition meshes as you would under any other circumstances. And then under baking options, you would scroll to where it says bent normal map right here. You check that box and click on this and make sure that you have everything that you want set in here. Usually the default options work fine, and then you can just close it and bake it out just as you would any other map. Real James Chan asks, in production, are object-based normals used for hard surface objects that don't deform? They can be, yes. There are some situations where, especially for weapon modeling, object-based normal maps are used because they tend to give slightly cleaner results than tangent space maps, and they're easier to bake out and get good results with, since they represent absolute directions instead of something that's relative to whatever your low poly is. So if you have to save a few polygons, it might be a good idea to render out an object-based normal map. Then you could apply it to your object space or your model in the engine, and most engines these days are pretty good about being able to transform things even if you're not able to deform the object. There's another question. Are object space normals less engine expensive than tangent space? To the best of my knowledge, they both represent the same amount of computational, weight, I guess you'd say. Because really what happens when you load a normal map into an engine is the normal map is converted to object space using some math that says, or that looks at the vertex normals of your object in the 3D scene, and then just modifies those object space normals based on the tangent space that you have. So if you went and you looked at, say, an object in a marmoset viewer file. Let's actually look at a marmoset viewer file and take a look at how this looks. So I can just go to my website because I have a few up there, and we can take a look at the one for this guy. Let me load that up real quick. Drag that over here. Might take a second to load. My computer's currently screaming at me because I have too many things open at once. Okay, so here's the marmoset viewer file for this Rockstar guy. And if I go to here and I select normals, you can actually see how normals are rendered in a game engine. This is what you would see if you tried to view the normals in Unreal, Unity, most proprietary engines. This is what it'll show you. And what it does is it shows the normals of your object and how they're being modified by the tangent space normal map. So engines always render object space normals, and then they modify those normals to account for the tangent space map. So it's always taking the object space normals of your object and then transforming them, no matter whether you have an object space normal map or a tangent space normal map. The next question is, there's a technique when you bake bent normal and then convert it to tangent. What can you tell about it? It's a very simple process to convert an object or bent normal map to a tangent space normal map, and I can actually do that right now. Here, let me go back to XNormal. We'll just minimize all this so it's out of the way. Minimize that. Okay, so let me just go here. Okay, so I need to select, oh wait, I'm in the wrong one. Here we go, Tools. So if I go to Object/Tangent Space Converter, you can load up, you really can load up any type of image into this converter. But basically what you're going to do is load your object-based normal map or your bent normal map into here along with your low poly model, and it will convert the object-based normal map to a tangent-based normal map based on the same math that's used to bake any other normal map. So let's load. Oops, low poly mesh. Let's load up our low cylinder. Let's make sure that smooth normal is turned on. Our input normal map, which is going to be the object space normal map we baked out for that cylinder, so this one. And then we're going to make a new output normal map, and we'll just call it cylinder normals x normal to differentiate it from the other one that we baked. Yes, we want to create this. And then you click generate, and it's going to take the information from the object space normal map, compare it to the tangents or the vertex normals of the low poly, and then output a tangent space normal map here. So let's take a look at the one we just made in Photoshop and the one we rendered out of Marmoset Toolbag. Oops, let me just open this in here. Let's make this comparison a little easier. There we go. So as you can see, they're pretty different because the way that Marmoset computes normals and the way that XNormal computes normals, they're slightly different, so you get different values. One of these was also rendered before we triangulated the model as opposed to after. This is after we triangulated, and this is before. So this is a tangent space normal map, not an object space normal map. Are there any other questions that you guys are interested in asking or discussing? Alrighty, well, if there are no more questions, then I'm gonna end the stream just a few minutes early tonight and go into the private hangout with the program members so that we can continue our discussion there. I will be doing another stream on Tuesday night, same bat time, same bat channel, etc., etc. And during the next stream, I'm actually going to be talking about baking and UVs and how some character specific techniques for laying out your UVs along with using the right UV space, like spacing between UV islands, orienting your UVs, using relaxed versus very straightened and square UVs, using UVs that go inside or outside the 0 to 1 space, having overlapping things. I'm going to be talking about a lot of different topics related to UVs, and then from there we'll have a little bit more discussion, and I'll give a few more examples of how how all those different things affect the final render, how it can affect how much detail you're able to get out of your objects, and After that, on next Thursday, I'm going to start talking about shaders, what shaders mean for character artists, different types of shaders, and how you can use specialized shaders. Thank you guys all for tuning in. Please don't forget to check out stuff that I have on, say, Twitter or ArtStation, whatever. I'm always posting information and updates and other stuff on social media. And yeah, once again, same time, 7 p.m. Pacific Standard Time. It's going to be 10 p.m. Eastern time, and it'll go for roughly 2 hours, and there should be some time for discussion and questions during that time. So I look forward to seeing some more of you there, and you guys have a good night. Thanks for watching.